Last lecture we derived very important quantities and relations between the invariance of a second order tensor and and the derivatives. And so for the first invariant, the derivative with respect to the same tensor, we showed that this is just an identity tensor. And for the second invariant, right, the one that has these quadratic terms in the traces, we obtained that we have the relationship when it takes derivative, so we obtain the minus transpose tensor itself plus the identity tensor multiplied by a factor which is the first invariant, so the linear trace appear here. Now for the third invariant, we just started talking about it, so things are a little bit trickier because we want to follow the same similar approach in the derivation as for the first and for the second invariant. Then we'll need to write all the components, and unfortunately when we have this these higher order terms here as a determinant, so we have a complicated expression that is not straightforward to take a derivative. Now still it's an important quantity that we'll encounter many times, and so we do need to find a way how to calculate the derivative of the third invariant of the determinant of a second order tensor with respect to the same second order tensor. So to that end, what we are going to do is doing the following. So we write, we look into that invariant. It is still this third invariant determinant, and now very similar to what you would do with when you work with scalars, right? So there is a change. So assuming that there is a function y of x, for example, and then you want to calculate how that function y changes at the point x plus delta x. The only difference now in what we're doing is that, okay, so these are not scalars here, but so here are not scalars here in the argument, and so we have a second order tensor, but the logic is the same. So we are calculating the value of that I3 of that scalar, of that determinant of function, if you like, at the point A plus some small dA change in A. And so then again, in a very similar manner as it was done in the calculating of these quantities with the simple function y of x, here we also have the original one, right? So that's the point where we started, at, say y at point x, right? So y3 at point A plus, so and here is our partial derivative multiplied by the change, by this increment d8, this differential, right? And of course, you can see that on the left-hand side, this is a scalar. So this part is also a scalar, right? So it's just a determinant of a second-order tensor. This is scalar, and of course here we also expect it to be a scalar, and then so of course you have this double contraction sign to make it a scalar, right? Otherwise, otherwise here when it takes the derivative of I3 with respect to d with the second order tensor A, then that will be second order tensor, and dA is of course also a second order tensor. Now so why we are doing this? So this I3 is a known quantity. Now what is not known is actually right here. So this is what we are after, and in general, so to calculate that, we would need to know this quantity on the on the left-hand side. So if we know that, and if we know this, so then we know this second term what is, and then we can deal with this double contraction with dA. Let's see what will happen there. So we'll start focusing on the left-hand side first. Okay, so what do we have in here? So this is I3, and when I write I3, what we do actually mean that there is a determinant of what is in the parentheses here. So, and what is in the parentheses is still another second order tensor, right? So it's just one tensor plus another tensor, doesn't matter how they're related. This is just another second order tensor. So it's one of the quantities of that. Now I'm writing it more explicitly again. So I3 is just a meaning in our language that take the determinant of that. So now we're going to do a few more tricks to rearrange what is inside just a little bit. And first of all, what I'm going to do is I'm pulling A out of these two guys. So so, and what will happen if I want to pull A outside? So then we will have identity here for the first term, and for the second term that will be A inverse multiplying dA, right? So just it's probably more clear if we just see what we do. So right, so what did we do from here to here? We pulled A outside, we obtained I here, right? So identity tensor. And so obviously if you multiply A and I and the identity tensor, that you will get A back, so you will get this term. Now if you multiply this A with the second term, so where we have A minus 1 inverse, so that will be also identity tensor, then identity tensor would multiply dA, and obviously what we get here is the dA is the origin. So we did basically nothing, we just pull from this tensor, the sum of these two tensors, we just pull A out of the parentheses. Now let's just rearrange the order a little bit, and the purpose of this exercise is such that we can write something similar to what we already have written for when we looked for eigenvalues, right? So okay, so what I'm doing here, so determinant is still here, this A still sits here, and the only thing that we have done is just we change the order of things here. So right, so this identity tensor going here, and of course it comes with plus, and you suddenly start seeing minus here, but obviously you have minus and you have minus 1 here, so basically this is still plus. So we didn't do anything, we just changed the order and in a weird way rewrote that as plus. So now why we're doing this? So we want to find in this parenthesis something similar to our eigenvalue problem, and in a way you already start seeing that that's actually what we have. So we just need to call this tensor as some kind of second order tensor, and then there is identity here, and the determinant also helps us. Now let's separate this A from what is here in the parentheses, right? So we can do that because it's a property of a determinant. So the determinant of this multiplication is nothing but multiplication of the determinants, right? So we can write the following, right? So we can just pull that A outside exactly right in here, and the rest is here, determinant of what is here in the parentheses I just copied here. And now we can forget for a moment about this that A. We'll keep it with us, of course, but now we need to focus on this part. That's actually what we wanted, and all the purpose of the manipulation in this previous line was to get to this form. Now this A inverse multiplying dA is nothing but some other second order tensor, right? So there is so we can give it a name, let's say B, for the similarity to what we already had. And if you remember, for our eigenvalue problem, structure was this when we tried to find. So we needed to find determinant of some second order tensor minus, and there was some unknown number eigenvalue, and multiplied by identity tensor. So And the only thing it was different from what we are doing here, we just required this to be equal to 0. So we don't need to do that here, but okay, so just to remind how it looked like. Right, so basically determinant of tensor B minus xi identity was written like this. So we never did all the calculation of that, but this is what you can derive if you want to do that. And so in case xi, if we say that all of this thing equal to 0, or all of this indeterminate of whatever is inside here, then xi will be the eigenvalue. But for us, we don't need to do that, right? So we just can use the same expression that that b minus some number xi identity can be written in this form. So we just going to use that, right? So we don't need to say that it's 0. And then xi will be minus 1. It's not an eigenvalue, right? So that's why I put here this what marks here, right? So this is it. So that would be an eigenvalue only in the case if that determinant here in this parenthesis will be 0, or the same will be correct to say if this expression will be 0 when we substitute xi minus 1, and instead of b we write this tensor. But we don't require that, so this is not an eigenvalue. We just use the relationship that we had once, that we know that if we take the determinant of second order tensor minus some number multiplied by I, it can be also written like this, and if we want that number to be the eigenvalue, we must satisfy it at 0. Okay. Let's quickly continue. So basically now we write explicitly what is this in this parenthesis, and we keep that a multiplying that, and then as a result we have this. So that a is out of the parenthesis, we don't deal with that. And then we basically look into what we have in 135, and instead of xi we write here minus 1 right here. So minus 1 to the power of 3 is still minus 1, with minus give us plus, so this is 1 here. And then we continue the same way, so it's the invariant, first invariant, but now what is our tensor? This is our tensor is here, so it's first invariant of a minus 1 dA, right? And that is supposed to multiply with xi square, and xi square was, for us, it was minus 1 squared, so plus. Everything is correct so far. And then the second term I2 of the same tensor, a minus 1 dA. And so now here we again get plus, because xi is minus 1, minus and minus give us plus. All very good. And this third one, okay, so no multiplication with xi, so no playing with the sign, so just plus. And so this is the third invariant of a inverse dA. Okay, so now let's look into what we had here in this part, in this or in the parentheses, what came out of the determinant that was very similarly written to our eigenvalue problem. Now, the first invariant is just trace A, and so that we can say that this will be a first order, and very similar to differential analysis, we always will demand that dA is a small changes, small quantities, and so we can require them to be as small as we want, or infinitesimally small, right? And then for us it's important to now to determine the order of how small things are here, right? And so this one is the linear one in dA, right? So this is a trace. The second one is already, this is I2, right? So this has quadratic terms in traces, and so it will be a second order in dA. And with I3, so this is determinant, and so for example we can think about multiplying by on the diagonal and having, so the multiplication, the order will be already even higher, so that will be third order in dA. And again, so this is just to summarize it here, so I marked with blue the second second order, quadratic in DA, and a cubic in DA for the third invariant. This will be important for us because basically we are going to say that whatever the higher order terms will just not deal with them. So because they are very small, right? So they are much smaller. They can be neglected relative to the first order linear term in DA. So, but just to make it formally, so we keep all this. These terms we must keep. So otherwise there's no change. And then the higher order terms we just call with the sign of higher order O sign here in DA. So whatever is quadratic and cubic terms are included in this term. Now, so basically, and okay, so now we say that everything that was here, that calculating of this I3 at the point A plus DA is equal to the initial value, right? So that A, that can be A3 at the point A, and plus this additional term here. So right, so basically we just came in here and multiplied that A with whatever is here is inside. So we multiply it with 1, so this that A here, and then the second term is preserved here, so that A I1 and of that new second order tensor inverse A multiplied DA, and higher order tensors here. So now so just to recall, so now just a little bit more of manipulation with this term. So I1 of this second order tensor new one in the parentheses is nothing but trace, right, of this, right, and and so we know, so this I1 of some, okay, so just said some other combination like this, and this is trace, and if you want to write it as a contraction product, or double contraction product, or double dot product, then we need to remember a little bit of a difference in the structure as we do that. So when second order tensor and B, another second order tensor is multiplied as a contraction, then you multiply their first and last indexes, right, and the neighboring the second of C and the first of B. In this case, when you multiply C and B, and this also transposed to that, so then you multiplied because of the transpose, you multiplied the first one with the second one, and so you must put this transpose here to make it the same as here, because the trace at the end will make the multiplication of the first index and the last index of these two. But we discussed that previously when we introduced double contraction, so now we can explicitly write what is here in the following way. So we can write is as A, if we use double contraction of that. So A1 is trace of what is inside, or it can be written as what is inside. I will need to put A minus transpose, because that is the transpose of that, double dot product DA. Right? Okay, let's just see how it's written. Just wanted to comment on that. So the first one here is just that A, so it's nothing but the third invariant A3A, and here we have also the A3A, so that's a multiplicator here, and then instead of the I1 of whatever is in the parentheses here, or basically trace of what is in here in the parentheses, we just use this property of traces and wrote it A minus transpose double contraction sign DA, and and so basically we use this property of hence this sign of the transpose. All right, so now dragging all the way without the higher order tensor, we actually can request that dA will be small enough so we can neglect the higher order terms in dA, and therefore the result for this is the following. So okay, so again our initial quantity here, right? So the calculation of that function at a point a plus a little bit of a dA, right? So, and that is equal nothing but what we derive here without the higher order tensor, so a3a plus a3a, right? So this is still a3a, a minus transpose double dot dA. Now with that we're almost done. So basically all this exercise was for what? So we wanted to calculate that, and basically we wanted to calculate this term on the left hand side of the 145. And so we're almost now what we know what this is. Of course we know this a3a, so we can now deduce what is the second term here on the right hand side. So as you can see, we basically can just substitute, if you like, the whole 155 here instead of I3 at the point A plus dA. And you also can notice that basically that the both have I3A, so we can remove both of these, and we can say that this term dA I3 dA double dot dA is equal this second term here, right? So that's the result. And now we can say, of course, that this must hold true for any choice of our dA, and hence so the derivative must be equal to what is here. So right, so that's the same operation that we apply with dA. So the only way that can be true for any dA will be such that this term is equal to this term. And basically that brings us to the end of this derivation. And so interestingly, when we take the derivative of the determinant of a with respect to a, or I3 with respect to a, so the result here is the same determinant a multiplied by a minus transpose. So this is, so we took I3, takes the derivative with respect to a, and we obtain I3 multiplied by a minus transpose. This is an important result that actually will be very useful for us, and many times save time on not repeating this derivation, the whole derivation here. And this is the expressions that now we can safely use because we know how to derive it.